All right, boiling point elevation and freezing point depression. These are both colligative properties, which depend on the number of particles dissolved, not the type of particle. And if you have a non-volatile solute, it's going to raise the boiling point. So it takes more higher temperature to get it up to 1 atmosphere because you've got less vapor pressure. So our equation, and the book writes it without the sub B's, and that doesn't matter. I just wanted to keep boiling point straight. So delta T is the boiling point elevation, so it's how much higher than the normal boiling point? So it doesn't tell you the new boiling point, it tells you the change. K sub B is the mole-al boiling point elevation, constant based on a solvent, and we can look those up. Okay, and we do really have a chart for those. It is on page 528 of your book, and the little m is molality. So remember, since it's kilograms of solvent, temperature doesn't affect it. And then look, we have the same thing for freezing point. It's the exact same equation. Let's put F's there. And you will find the K sub B and the K sub F. They do have those there. So we can use either of these to find a molar mass. So we've got, we want to calculate the boiling point elevation. Well, we want to calculate the boiling point. So we need to know the normal boiling point. And we find that urea is, of course, not in the chart that is in your book. Could have picked a better question. All right, let me pause this and find the information for urea. Okay. Again, I am not reading these questions properly because we need the boiling point of the solvent. And what's the solvent in this? It's water. So we know the normal boiling point is 100 degrees Celsius. And when we look up the KB for water, it is 0.51. And like all constants, it has sort of complex units. All right, so now we need our mole fraction. So our mole fraction, not our mole fraction, our molality. Maybe I need to stop doing this. All right, is going to be our moles of urea over our kilograms of solvent. So our kilograms of solvent is 0.15 kilograms. And to find our moles of urea, we have to take our 27.0 grams of urea and divide it by the molar mass. So urea is made up of nitrogen, which has a mass of 14.01, and we have 2 of them. And hydrogen, 1.01. We have 4 of them, so we've got a 2 inside and outside the parentheses. Plus carbon, which is 12.01, plus oxygen, which is 16. So we have 60.07. So 27 divided by this, second function to get our answer, means we have 0.4495. And we just hit divided by, pops the answer on, and we do our 0.15 kilograms of water. And we have 2.9965. And this is moles per kilogram. You can see why constants have units like they do. They are designed so that stuff cancels properly. Now don't worry how many significant digits you wrote down there because you're just going to hit times. Computer calculator is going to use the whole thing. Multiply it by that 0.51 and we get, now's when we'll round two significant digits. And we've got 1.53. So that is the change. So the new boiling point would be 101.53 degrees Celsius. So let's do another one. All right. We've got a lot of nice background information about the compound, but that's nothing that we need to do the problem. So let's look at what we need to do the problem. We've got 1 gram of this Respirine. We've got 25 grams of camphor. We've got the freezing point depression. We've got the Kf. We want to calculate the molality and then the molar mass. So delta Tf equals Kf times the molality. I'm just going to use a sub R for the Respirine. Okay? So delta Tf divided by Kf is going to give us our molality. So we have 2.63 degrees Celsius divided by 40 degrees Celsius kilograms per mole. It's going to give us our molality. All right, so we have 2.63 divided by 40. So that gives us 0.06575. Let me pull my calculator up and make sure that's it. 0.06575. All right, so what are the units on this? Well, degrees Celsius cancels. I wrote this wrong. So we are dividing by kilograms per mole, so that flips. So we have moles per kilogram. So that is the molality that they asked us for. So if we were recording it for an answer, then we would go ahead and round it to significant digits. But to use it in the next problem, we want to keep it like that. So what do we want? We want molar mass. And molar mass is grams over mole. We were given 1 gram of the Respirine, so we need the moles. So the molality is going to give us the moles. We know that we have 25.0 grams of the solvent. Turn that to kilograms. And what is molality? But it is moles per kilogram. So grams cancels, kilograms cancels, and it's going to leave us with the moles to plug in there. So 25 divided by 1,000 times, I can use my answer from the line above, and I get that many moles. So 1 gram divided by that many moles gives me my molar mass of 608.